So if we carry through that ds differentiation, right, you get this result here. This is just carrying out that differentiation. And it's important here that you go, right, this is your change in pressure along the streamline coordinate, right? And then this, right, it's important to notice that there's a u squared here. So this is sort of any change. So any deceleration or acceleration of the velocity along the streamline contributes to this because of the squared part. It's not, it doesn't have a negative sign in it to only count. It won't only count decelerations or accelerations, right? It has this square in there. So that's sort of any change in velocity along your curved streamline has this, right, gives you a component here. And then this, right, this is a change. So that is the change in elevation as you go along the streamline. So those are all the things we have to play with. All of this begins, if we talk about streamline bodies, is to say that, right, is you have to start off by saying this, and that would make this go away. And that gives you just a binary relationship between these two things. But again, you got to be somewhat, you got to be somewhat motivated to say these things. So, right, you just say that this, right, that the change in elevation along the streamline doesn't change too much. So clearly, I think for a streamline body, that's okay, and everyone's okay saying that, because if this is a z, right, think of s. I mean, here's your s right here. This could be s equals 1. This could be s equals 1. I mean, you could parameterize it any way. But, right, so then, right, so that'd be like the length, right? This is sort of the height of your, right, of your streamline body. And then for, right, s really could be, right, manipulated like this. So, you know, you can make sort of checks in your head if you just want to see, well, is that really 0? Because, right, you scales, right, as this h over L. So for an airplane wing, right, this is okay to say something like this. And for most streamlined bodies, it's going to be okay to say this pressure distribution thing. But, you know, there, you could clearly have some things where, like, what if it was just this in the flow field, right? I think everyone maybe would have the same expression or same understanding that I can't really say that, but it just depends how big is it going to be compared to the other ones. But it's still a check you could do, right? Because here, right, it's the same expression, only now you have this like height or z height, and really it's over 2, right? Because we clearly should do that. So really the change is going to be, right, over 2. It doesn't really matter though, but like this gives you an idea of like when it's really valid to maybe like throw that term away. And in fact, even if it does look like this, you could compare it to these other terms and you would actually see that, like, well, I mean, it's not the biggest contribution to this pressure difference, but you know, anytime you cross a term off in an equation, I always just kind of like to say, well, can I really do that? And really this idea of just scaling and just seeing what your differential terms look like in terms of measured values helps you do that. So I think that's super important. Okay, but let's say, you know, I've done my check on dz/ds, and I can say, okay, it's gone. You get the very classic, actually I'm going to erase this top one, even just write the whole thing out. You get this very classic relationship for, and then if I expand out that, right, if I expand this out, you get this classic differential relationship. This comes because, like, right, 1/2, if this is squared, you could do the product rule. And get something like that. So just making clear that that's going to be equal to that. And then it was addition on these sides, so this gives you now this negative sign. And that's pretty important. That actually draws a lot of conclusions that we have to talk about in a sec. But this is the basis of this. Any sort of body, right? If you look at a streamline, and at this point, right, you're going to have to look at the U. Knowing something about U of S will tell you something about the pressure along there. Likewise, knowing something about the pressure will tell you about the acceleration right there. That's the importance of throwing away that dz/ds, because if you know something about the free stream velocity, you know about the pressure. Another weird one is if you know about the pressure, you would be able to tell something about the free stream velocity. More commonly, you know something about the velocity, so it informs you about pressure. But, right, it's likewise either or. So just from that equation, you get these important cases. Let me just put it maybe off to the side, because it just references the same equation. Okay, so given ideas about velocity, infer things about pressure. And this is the classic case thing you go through. So, right, one case is the acceleration case, right, where du ds is greater than 0. That's acceleration. So this number being greater than 0, this is negative. This is now positive. So now I get, right, a negative. Now I get a negative quantity, right? So this implies now that the pressure now decreases. So this is called favorable. Right? This is a term you should be familiar with later on, is favorable pressure gradient. Favorable means it's less pressure as you get somewhere. And I just wonder where that terminology comes from, but right, so the favorable pressure gradient has implications about shear stress. So so ds dz being greater than 0 also means you could think about dr, that this now is increasing. So that increasing implies that this is now less than, right, this is decreasing, so I'm getting, right, so I have my boundary layer. Boundary layer is shrinking if the Reynolds number is increasing. You've already seen that for the external ones. And then from the same thing, you get this idea that, well, if I have favorable pressure gradients, that means that the shear stress along the wall along the streamline is now increasing. So I think that's where this term favorable actually came from. But I looked in your text; it doesn't say why it says favorable. But that's my idea: is you'd have acceleration involves decreasing pressures, which involve something about your boundary layers, and that means that your shear stress is increasing. So that's just case 1. I'm accelerating. So obviously the other one is you have case 2. And that's decelerating flow. So, right, of course, it's the same thing now. Now you have something called adverse pressure gradient. Given this terminology, the adverse pressure gradient. Now, the adverse pressure gradient comes around because, by the same reasonings, right, When this happens, shear stress along the wall is now decreasing. Right? Otherwise, also you can think of it as now an increasing boundary layer as I move along S. So I think adverse comes around because this shear stress is decreasing, and you get this situation where you wonder what happened if it goes down to zero, if you have no shear stress at the wall, and that's problematic. Those are two classic cases you get just from that equation throwing out dz ds.